Hello friends, I am DEVANSHI from MIT College of Engineering, Pune, and in this video I am going to discuss about Multimedia-IP image and video codec design methodology. So the things that I am going to discuss in this are system analysis, architecture exploration and in-depth design alternative overview, application specific architecture and design issues and techniques. So before hardware architecture design, system analysis was the most important step to have insight into the design problem designers face. The goal of system analysis is to find out the bottleneck of a video codec design so that designers can focus on it and get an optimal design. The basic data that we want to get from system analysis are computational complexity and memory access. There are many different approaches and tools for system analysis. Though the analysis results differ as the software is running on different platforms, the analysis data still provide designers a good starting point to understand the complexity of system and each module. The profiling tools can be, for example, common runtime profile tools on workstation and PC, instruction profiling tools, and etc. The design space of signal processing ICs is wide and colorful. Although some variants may exist in different architectures, design alternatives can be mainly classified as follows. The two extremities of the design space are processor-based design and fully application-specific IC design. In between there are architectures such as platform-based, FPGA, digital signal processor, multimedia processor, application-specific DSP and some others. Now talking about the pros and cons of the platform-based processor. Processor-based design provides better programmability and lower performance for video coding, while the ASIC design provides best performance with a little flexibility. General purpose processors are too general to handle the loading of your video coding. Application specific instruction or dedicated accelerators can improve its performance for video coding. Approaches like the application specific DSP and video and media processor at the same time. General FPGA also try to embed more dedicated arithmetic units to boost their capability. Application specific architecture. There are many arguments over the pros and cons of different architectures. Basically, optimal architecture should be depend on application and the overall system considerations. The guideline is to provide just enough computing resources at the lowest design cost and time. An image video specific architecture is optimal for computational performance, even for a processor or platform based design. Designers also have to understand the design of dedicated architecture so that they will be able to enhance the processor architecture. Design issues and techniques. For image and video application, the speed requirement is usually the most urgent issue. Actually, for online video application, the first priority of an implementation is to meet the real-time specification. Since there is a large amount of data to be processed within a tight time constraint, general processors which execute the computation sequentially cannot afford such high computational load. Only by raising the working frequency is not a good approach to solve the problem. Working fast but not efficiently is also not an optimal way. Also, high power consumption is a problem at a high frequency, especially for battery power portable appliances. Therefore, for image and video codec design, ASIC designs usually do not pursue very high operating frequencies. On the contrary, designers look for some more efficient architectures to be operated at lower clock rate, example SIMD and VLIW. Area. IC designers always look for a compact architecture since smaller die area means lower cost. A more compact design have a better competitiveness. Area is used to trade with frequency. Parallel architecture results in a higher area cost, therefore, hardware utilization is index the designer should take care of and check. Simply duplicating multiple processing elements and memories may not be an optimal way if some of these resources are with low hardware utilization rate. The optimization goal should be just enough parallelism with as high as possible hardware utilization. Algorithm level optimization, hardware sharing and polling are example techniques for chip area optimization. Power. The power issue becomes one of the most important problems in SoC design. As a process development, a chip can provide more and more transistors but allow power consumption in chip will not increase. The emerging portable multimedia device asks for more restricted power consumption. Besides, the heat due to high power consumption will also cause reliability problem. To cope with the power problem, designers should be carefully examined not only in architecture level but also in algorithm and circuit levels. Actually, the higher level optimization usually provides more gain in power saving. Developing fast algorithms with lower complexity and algorithms with lower data bandwidth are examples of this. At architecture level, designers have to look into the detailed operation of each module, or even each gate, and its power consumption behavior. Higher hardware utilization architecture will be more powerful efficient since the higher power will not be wasted on idle gates. Memory is also a big source of power consumption. Therefore, memory hierarchy management will play an important role on a lower power design. At last, the algorithm and architecture characteristics can be combined with circuit level techniques such as clock gating and dynamic voltage scaling. Bandwidth and storage. Memory bandwidth and on-chip memory capacity are limiting factors for many multimedia applications. Today, in many designs, on-chip memory has already occupied more than 50% of total chip area. Good memory management and area power and efficient memory implementation become important for a successful SoC solution. The memory management is to provide an efficient memory hierarchy that consists of off-chip memory, on-chip memory, and resistors. Off-chip memory, usually DRAM, offers a large amount of storage size but consumes the most power. The off-chip memory and I/O access may dominate the power budget. The embedded DRAM is developed to reduce I/O access by integrating large on-chip DRAM. However, the embedded DRAM and many physical design challenges still need to be solved. Besides, embedded compression techniques can be applied to reduce the off-chip memory bandwidth and size for video codec design. The on-chip memory usually implemented by STEM provides faster access and less power consumption than the off-chip memory, but the memory cell size is much larger. Resistors can be faster than on-chip memory and provide more flexible data storage. However, the size of resistor is the largest. Resistors are more suitable for the implementation of smaller size buffers. Memory management can be organized from two different levels, algorithm level and architecture level. The embedded DRAM is one kind of circuit level improvement. But even integrating large embedded DRAM, the access power is still larger than the smaller on-chip SRAM. The algorithm level memory hierarchy optimization is to modify the coding system algorithm to improve some system parameters like power or area, and some other parameters like coding performance become the trade-off. On the other hand, the architecture level memory organization can optimize the memory hierarchy from the modifying hardware architecture. Perceptual quality. Video is for human eyes, not for computers. The perception of human eyes determines the quality requirement of video signal processing. For digital video, larger dynamic range of visual means better quality, but with larger hardware cost. Designers have to make decisions based on product specification. Another good reference is the saturation point of quality improvement when the bit width is increasing. Besides the trade-off between area cost and quality, computational complexity can also be lower at some cost of qualification degree.